All right. So my name is Adam Benedict. I'm going to present on AC Schematics. So this will be the last section of the drawing review. And we covered DC, covered one lines, and so AC Schematics falls right there with AC and DC. It's typically developed and finalized during the preliminary design phase. Right before you head into the wiring diagrams. So purpose of an AC schematic is to kind of take that one line, that relay one line, and expand on that. Really focusing on showing the proper phases and then adding more detail to all your primary equipment as well as your relays. So here we're going to look at this one line, this relay one line, and kind of zoom in on this section. So keep in mind what you're seeing here. When it comes to the relay one line, we got a breaker, switches. This should all look pretty familiar and based on the relay one line review. And then we have our CTs as well. So you see our CTs, and then here we connect into our relays. We're showing some phasing all on that, this node here. So when we zoom in, what we're looking at when it comes to the AC schematic, I'll try and zoom in a little further. Didn't make it much better, but we're looking at phase 1, phase 2, phase 3, and I apologize if it's hard to read. And this is going to be vital as we carry it through, but we're seeing phasing. Our switches are broken out, 3 phases. Our same thing, our CTs are broken out into those 3 phases. We're seeing bushing numbers on our breakers, single phase equipment shown on the proper phase here. And then we're starting to show more detail when it comes to the connections, taps, terminals. Our relays are broken out likewise, and then we're showing more detail on those test switches as well. So overall, just more detail, and kind of each step of these drawings as you look at this adds that extra layer of detail until you're basically wiring and programming the station up. One line symbols versus 3 line symbols, there's not going to look a ton different other than just bigger with more detail. You can tell based on the one lines that this is your disconnect switch. The dashed line means gang operated. Here's your breaker. It's just adding the bushings. And then you're seeing your CTs with some more detail, even with some taps and phasing info, wire label info. Breaker bushing numbers. They're always numbered the same way. This is a IEEE or NEMA standard. 135 is always on the same side. 246 is always on the same side. When you're looking at it, make sure to reference the vendor print and know not to mirror the breaker. And this is a common drafting mistake where, if you need to kind of flip where 1 and 2 are, just know you can't mirror it. Otherwise, the breaker's being installed upside down. So in this case, if you wanted to flip the breaker, you want 1 and 2 to be on the top here. So it would be 1 up here and 2 over there. You should never see 1 down in this lower right. And definitely it's a check that should happen throughout as you're going through the design, just to make sure that a drafter, a designer didn't accidentally just mirror it, not knowing what the physical repercussions are. So moving on to some more one-line symbols. If we look, we have a transformer. This one's a transformer with 2 secondaries. So you have 1 primary. This is your circuit switcher here. So you see your circuit switcher here. And ideally, when you're setting up your AC schematic, and they're not doing it here for one reason or another, but you want your one line and your three lines to be oriented the same. So where you have a circuit switcher on the right, here you have a circuit switcher on the left. So, a good design practice. I'm sure they had their reasons for it, and there's reasons to deviate all the time. But ideally, that's how you'd want this circuit switcher on the left, or vice versa, you'd want this on the right, based on the one line. So as we're going through this, we have our lightning arrestor, surge arrestor here, which is good. It should always flow like that. Here we're showing our bushings. The one line didn't show the bushings, but that's fine. Again, these are going to identify where your CTs start. If it's a slip-on CT, usually you'll see those on the other side of these symbols, indicating that it's not in the bushing itself. These are usually in the tank of the transformer, attached to the bushing, where a slip-on would be on top of the bushing. So that's why it would be shown to the left of these H1, H2, H3. And then moving down, we see all these are important connections, and we need to verify them. Not just against the one line, but definitely against the electrical arrangement, to make sure that it's going to be installed the way we're installing our protection. Let's see, moving down, you see our secondary connections line up, and basically all these connections need to match, right? That's the whole goal. Every time you're checking a drawing, whether it's a one line or a schematic or wiring, you should be checking against something, right? What's your basis for doing this? You're not doing any one of these drawings in a vacuum. If you're doing a one line, you should be basing it off of protection standards, or in your scoping document and your planning document. That's where you're trying to verify all the high level details. And then once you're in schematics, those high level details should be locked in. So now you're trying to really hone in on the three line connections. Where is this connected right? Is X3 to Y3? Is that connection correct? Are my CTs shorted properly? Are my single phase equipment installed on the right phase? So that's why each one of these is done in a phase. So you get this done, and then you move on that. And the design flow has been this way for 100 years, and it's really methodical in how you approach this, and that's a big part of how young engineers acclimate, I guess, to the field, is learning the design flow and what to look for at what stage. So just something to keep in mind. Important to confirm standards. This side's gonna look familiar. It's how we live and die in this field, is making sure we're confirming the standards, and be that industry standards or client standards, or just good design practices. But you see here, these switches aren't actually the same. This is a center break switch. This is not necessarily a center break switch. So those two aren't lining up. Here's a good example. You have a center break switch, motor operated. Here's a center break switch, motor operated. Here we have a circuit switcher. I forget why they call it FIS, but and then moving down, this is what they show in their AC schematic for a circuit switcher. And then gang operated switch. These are, sorry, this isn't this is the individual switch, not gang operated. You'd see a dash line through it, or a dash line through there as well. Phasing, I hit on that, but this is the number one design coordination issue between protection control and substation physical design. So here you have what's called an EA. You see here we have our phases A, B, C, A, B, C. It's either A, B, C, or 1, 2, 3 generally. And what we're looking for as we go through this is does our phasing match, right? So you have A on the left here, you have A on the left here. That's great. B, B, C, C. And then you want to step down through this. And this check needs to happen not just in schematic, but also in the wiring, and then even the IFC review. And then good coordination between the PNC and design and the substation design is really important. Making sure to let your physical design engineer know that any change to this diagram, this EA, as it relates to phasing and equipment placement, is going to impact your schematics, your wiring, maybe your relay one lines as well. So that takes a lot of practice and coordination. Phasing, it can differ between substations and utilities. And beyond that, this isn't a good example, but as there's line takeoffs, let me show you right up here. So as these lines go out to different stations, there could be phase rolls as well coming into the station, which could impact certainly our phasing. We could be expecting phase A, but the transmission line engineer ends up bringing us C into the station. And when you're talking a line diff, that can really screw up your protection, right? If you're trying to line up phase A to phase A at the remote end, and you're actually looking at C, that's going to be a problem. And then once you interconnect as well, pay attention to that, whether it's A, B, C, 1, 2, 3, or even between systems. I believe CMP, they have phase A, B, C on their 345 and 1, 2, 3 on their below, 115 and a below. But the phase 1 and phase A don't line up. I think phase 1 is B, and so that's something to be on the lookout for as well. Not assuming just between voltages you're going to see 1 is equal to 1 or 1 is equal to A. And then obviously being on the lookout for that single phase versus 3-phase equipment. Phasing. So this is really focusing in on your single phase equipment. This utility isn't a great example, and I'll show you at the end, but they don't go into a ton of detail on their AC schematics, which is good and bad. They're very standardized and locked in on their practices. It's a very large utility, but for them, they're just going to put A, and we're making sure it matches A here, and then we're also looking on the EA as well to make sure that is A. But they're not going to show it actually connecting into the bus work. This is a different utility, and this is going to show more of the bus work. So this is a traditional 3-line AC schematic. And here, what we're looking at is our wave trap. It's typically on one phase. Here they chose the center phase B, and what we're going to look for is it's not shown here, but making sure that's on phase B, as it says right there. So I'd be looking to say, okay, A, B, C, that's on B, that's great. And then I'd double check the EA as well. And if it's not, and you want to look at the remote end beyond that, because if they have a wave trap in their carrier equipment, their line tuner on phase A, this wave trap is useless, right? So that's where you have to expand beyond your current set of drawings. And that's the sign of a good relay engineer, is looking and saying, okay, what am I impacting here? What's the impacts beyond just this wire, this relay, my station, what remote end impacts? So here I would go to Cypress and be like, okay, are you on phase B? I'm on phase B. Okay, good. Sometimes that requires talking to other consultants, other utilities, but that level of coordination is a big one. Current transformers, they allow, and we've talked about this, so I'm not going to spend a ton of that, but they allow the high voltage measurement to be passed along to the relay. Certainly you can't plug in a 3000 amp bus CT to or 3000 amp bus current into a relay. So that's where we use the CTs and tap it. And then different accuracy classes too. This is where you would work with your settings engineer to see where the saturation level is and make sure you're specifying the right CT, whether it's C400, C800, C1200, and then polarity markings. And I didn't put them in here because I know that's taught, in AC and some of your other classes, but just know that that's another one that gets screwed up commonly. Here's an example of a nameplate. This is a really good picture. Half the time I'm in the field, these pictures are hard to take with the sun glaring on them, and they're usually faded or they're stamped and hard to read. So, but this is a good example of what we'd see in the field. So here you see your thermal rating of 2, your accuracy C800. These are all important when you're looking at saturation. And then here's your CTs and how they're arranged. So this would be your bushing 1, 3, 5, 2, 4, 6. And then you could see 1Y is closest to the bushing. Here's your breaker operating mechanism. And then 1X is on the inner. So usually you hear outer, inner, and then same thing. The Y here is always on the outer, the X is on the inner. And if there's a third, it'll be out here as a, the Y would be the middle CT, the Z would be on the outer, and it's always called Z when it comes to breaker CTs. Transformer CTs are labeled a little different, but. And then here it's important to take this picture when you're out in the field to say, okay, it's 3000 to 5. What are my taps? Where can I tap, right? If I need to tap it down to 1205, I would connect it to X2 to X3. And it's important to know while we're looking at this, if you are shorting a CT, always short 1 to 5. If you were to short, say, X2 to X3, you would develop a potential and potentially cause a flashover. Not good. So if you're shorting a CT, full ratio. If you're wiring it out, you can tap it down, and that's allowable. It's allowed. CT configurations, they can be found in 3-phase and single-phase configurations. 3-phase CTs can be found on equipment bushings for relaying. Single phase generally found on transformer neutrals or internal transformer relaying. It could be like a very tertiary you're trying to monitor. That's an example of that would be 3-phase too, but trying to think of other single phase CTs. Metering could be single phase, but yeah, 9 times out of 10 it's under transformer neutral. Or it's used for, you'll see it for transformer monitors too. They'll have a single phase CT or LTC, your low tap changer. Delta versus Y CTs. These were common, the delta at least, were more common in your transformer diffs when you're trying to account for that phase shift between a delta Y transformer. Where on the delta side, you would connect your CTs in a Y configuration, and then vice versa on the Y, you would connect your CTs on a delta to offset that 30 degrees phase shift. But you'll still see delta CTs occasionally, but not very common. Aux CTs, usually this is to help provide some isolation for primary and secondary. If you only have one CT on say a transformer, but you have 2 sets of protection, an aux CT could help you achieve that galvanic isolation. It's not perfect, but it does provide a little electrical isolation. And then so what else do we DFRs, digital fault recorders, they use OCTs, basically anything that doesn't take a if you're not doing a 1-to-1 ratio, that if you're doing a 1-to-1, sorry, let me start over. If you're doing a 1-to-1 ratio OCT, that's generally for isolation between your primary and secondary relaying. If it's to step it down, it's usually for something like a digital fault recorder, or an RTU, or some type of monitoring device. Standalone CTs versus bushing CTs are, let's see if I, bushing CTs you'll see here and here. So they're installed right on the bushings. A standalone CT would be down the line. So usually have it connected over some bus work or strain bus, and have it go through the CT, and then you'd have a terminal block down at the bottom of the standalone stand. And then likewise here, you got, like I said, your CTs are usually in here, and I'm not sure, I don't see the neutral CT, but I'll see if I can find a good picture of the neutral CT for next time. Ways to screw up a CT: leave the CT open. That is so bad. Yeah, don't do that. And that can happen a number of ways. Yeah, I was viewing a set of prints, and they left off one of the CTs in their design. It was in the vendor prints, so I made them put it in the design, and they got mad when I marked it up and dinged them on the scorecard. But they're like, well, it was shorted, so you shouldn't have given us downgraded us in our score. But I was like, well, okay, but if we're going the field, they're going to base it on your prints generally. So, that's one way to screw it up, is just ignoring it. I think a transformer in Vassalboro was damaged for something very similar. So, using incorrect CT ratio, this is one with that coordination between the PNC design and settings. Having the wrong ratio is going to make their settings invalid, which would cause issues. Connecting the wrong polarity, certainly on a diff circuit, that would cause an issue. Thinking you're getting a positive current and you're getting the opposite, you're getting that negative reading. Parallel connections. There are a few instances where you would have parallel CT, but if you're trying to read the same CT value, you want to make sure it's in series. I've seen parallel CTs to help with saturation before. So there are a couple instances, but you got to be very intentional with that. Generally, you want to make sure all your connections downstream of the CT are series, unless you're summing it for a node, which I can show you. We're going to take a look up here. So here you'll see comes in, that comes in. So you have your, oh shoot, what happened? Okay. So here you have your CT come in to a meter, and then series on to, looks like your 11, so it'd be your breaker relay. So that these are all in series. And here this reading comes in, and this is where they're paralleled in a sum. And then this would be your line relay. So they're summing basically this current and this current to add up to this line. But this breaker relay only cares about the current coming out of here. So that's where you got to really look at it. What does this relay need to see versus this one? This one doesn't want both. It's only looking at this breaker. So it goes through, and then this line relay needs both values. So that's where you would parallel those up. Connect the relay to the wrong CT. I think that one's kind of obvious. And then multiple grounds on the circuit can cause some strange readings through adding some pass through ground. So definitely make sure all your CTs only have that single point of ground. And that, I believe it's in the standard, but definitely good practice is the first point that that CT cable comes in. That's where you install your ground. So that cable comes out of the breaker, it goes into the control house, and that first cabinet it goes to, that's where you would see the CT ground. That's a pretty common industry practice. This is a high impedance differential, and I did want to talk about this because it is different when it comes to the CT connections in that there's some good practices, I guess, that I want to pass along. So a high impedance diff works, obviously there's a high impedance value. So what you're going to see here is all these get summed, and basically they use a resistor to they convert that that current value to a voltage value, and that's actually what you've set this relay to. But when it comes to our design, all these cables, since they're summed here, they all need to be the same length. So usually what you see, let's see if I can get a pen. So right about here, you would see a junction box. So this cable, these relays would be wired to this junction box. This would be that, there, etc. down the line. And this junction box would be installed centrally to the all these breakers, with the goal being each one of these leads would be the same, as close to the same length as possible. If it was this one's super short, this one's super long, you're gonna have a difference in your currents, which will result in a difference here. So you want to have these summed into a yard junction box, and then have a single cable run back to this 587. And then it's important to have these lockouts here installed here. So when this does sense a fault, it'll trip this lockout, which will short out your CTs. Otherwise, you'll burn up this relay. The high impedance diff is not as prevalent, but it is super cheap. So I know a lot of developers like to use them because they're only, I think, like $500 to buy. So, and they work great, but the disadvantage is, all the physical constraints, and it's harder to add on breakers knowing that this junction box might need to be moved, or could cause you to change the margin in your settings as well. The other type of differential, and this one's very common, definitely when it comes to transformer and bus as well, is the low impedance. And this is just wired as you would expect. I guess you have single connection from the CT into the CT input from each breaker. And at this point, the limiting factor is how many inputs can I have, right? Here, you're limited to 3 based on this, unless you can add a card or buy a new relay. But you're not worried about shorting them out. You're not worried about you're a little worried about the difference in line length or the cable length, but not to the same degree as your high impedance. Here, you're more worried about saturation being the difference here. PTs and VTs, they allow for a measurable voltage to be taken, and I think this is getting a little repetitive, so I apologize, but a typical PT VT ratio depends on the voltage class, and the secondary is generally always a 66 volt, somewhere between that 64 to 69 volt range for the lower output, and then the higher ones like 110 to 115 volts. So that's the goal of the VT ratios. Thermal ratings, you are looking for the thermal ratings. Haven't encountered many issues with this, but definitely should be looked at, especially if you're touching something with electromechanicals. They generally have a higher burden, which in which the thermal rating is more of a factor. PTs and VTs, they could also be used for metering or AC station service. Be cautious using them for AC station service because it can impact your the accuracy of your reading. There's different types: pad mount, overhead, high voltage PTs, definitely overhead, and these would be like a stand mount. Those are the most common. And then know that PTs and VTs are used for metering 100%, and then they're used for generally anything below 100 kV, so like 69 kV and below. CCVT is used for generally anything 115 kV and above, sometimes 69 kV, being that they're cheaper, but they can't be used, generally they can't be used for metering. They don't have that accuracy, but they are cheaper. Here's the two common configurations where you have a Y connected. Yeah, you have your Y connected right here, and then here you have that. I always get them backwards. Broken delta. So this gives you at 3V0. It's used for definitely on. I see it most common on tertiary or station services that are ungrounded. So this would be how you would detect that ground fault. And then here's another configuration to get you that 3 phases. Not super common. It's generally if they're trying to save money on transformers. So usually you see this Y connection here. Here's some pictures. Here's your stand for your CCVT. Here would be a station VT. This looks like a 34 kV station, and then another overhead mounted VT. So ways to isolate. We talked about FT switches. Yeah, I think it's important to go over them again because it's another way to screw up your AC circuit. But all relays need to be tested before they're put in a service, and then anytime you're doing these designs, particularly on a CT and a PT, you should have testing in mind, right? How am I going to isolate this device? How am I going to disconnect my relay if it burns up, and do it safely so we're not electrocuting anyone. And I guess high level, the FTs can be one set of switches or 3 configured for currents or potentials. Then keep in mind the different colors that the client could use. Here's an example of a current shorting, and know that this is designed to be make before break. And this would go the same for the PK blocks. But so if as these are opened, and it's easier if I was in the classroom with one of these switches, show you. But as it opens, it makes contact here. And then this one's always connected. So before this, if you were to open it before it leaves this terminal, it's making contact here, shorting out where your CT is. Let me draw it down here. So you would have your CT connected down here. And then as this opens, it makes contact, shorting, crossed before it leaves that terminal. Fun fact. Then we looked at the configurator. I'm not gonna run through that again, but just here's the website. This is the FT19 rear connected R. So the 19 is the set of 3, The FT1 is the SETA 1. PK blocks, I generally see these with that high impedance diff because it's really good at shorting everything out. And you put in these shorting strips, and this is an important thing to look at during testing your machining or panel checkouts. This is one that you should always look at because it's easy to not install these. So you want to be looking to make sure those are installed in the right sets. And then basically this is mechanically operated. So as you pull that out, this little bar goes up, makes contact with this and this instantaneously, super fast, and shorts it out. Secondary connections need to ensure the secondary winding of whatever piece of equipment is correctly connected. And we're looking at all the ratios, burdens, wire sizes. That's one we haven't talked about. Wire size can dictate whether or not your relay is going to saturate. So for a CT, I think the smallest I've seen installed is a 12, definitely no 14 gauge. But most utilities use a 10 gauge for all their CTs to help lessen the burden. And when settings comes, it's not uncommon. I shouldn't say that. It is uncommon generally to run into it with a microprocessor relays, but you could encounter a situation where you might need to double up on your cabling to account for saturation to help. The lower your cable impedance is, the lower the burden, which could lessen the chance of that CT saturating. So it's important to verify, the configurations, your burdens of your relays, and work with your settings engineer to make it accurate. Secondary connections is just more examples of here's your open delta. So I guess the other one was a broken delta. So here's your open delta configuration. And it's important to check and read your manuals on how these relays should be connected. I know GE has some important grounding info within their relay manual. So I'm not going to repeat it because I don't know it quite off the top of my head right now, but I would definitely go to that section of the manual and look it up next time I design one. So, all right, so that's it for the presentation. Let's see if I have some good examples. So let me zoom in. When I was talking about that utility before, this is really what they show for their three-phase AC schematics. So you see, they basically put the AC connections on a DC print, and then they have phases A, B, C shown. And this takes that extra level of verification where you don't have a breaker. You're not showing your lines, your breakers, your transformers. So you really need to bounce this against the one lines, the vendor drawings, and the EAs to make sure your phasing is right. You're using X instead of Y, and then what side you're on is accurate. It's not my favorite way to show it, but it is what it is. So let's see if they got more examples here. So yeah, another CT connection. I think they're PTs they show. And yeah, here's the PT connection. So they show a little more detail. Again, this isn't connected to the bus work. So, we got phase A, phase A, phase A. I'd want to check that against the EA. And then as you step through, we have our FTs out in the breaker, out in the junction box. And then we're showing our cables, our cable labels. And then here's that ground in the first cabinet in the control house. And then here's your FTs and your relay. So it's in the voltage. Here's another one. At this station, they actually use their VTs to power. There's not much here. It's a little switch. It's like a set of motor operated switches. So they use the VT to power the switches here. So not much going on. Let's see. I think I grabbed some more. All right, this is a different utility showing more the info that I like to see that you guys will probably see as well. Here we see there's our operating bus. Then we see our phases A, B, C with our switch shown 3-phase configuration. They even show future equipment. Stepping down through, I want to make sure A is connected to A, B is B, C is C. And then we have our circuit switcher. Here they use the wrong symbol. These just look like grounds. I didn't do it. It was another consultant, but this just looks like they're grounding out the station, but this is actually LAs or surge arresters. So we fix that symbol, and then we're verifying H1, H2, H3 against the vendor prints. Looking for grounding. Here's where it's connected right in the first panel inside the control house. You're making sure you got shorting FTs here. This is all connected, and then there's a return back. You're also looking for any way the CT could accidentally be opened. There's a utility in Massachusetts where they don't use shorting terminal blocks, and it always causes me heartburn to work on that. But so where they don't use, these are shorting terminal blocks down here. So this utility would have just regular terminal blocks, and a shorting terminal block. Let's see if I can get you a picture. They have these screws to help short out the. You would put a screw between 1 and 5, and once you connect that, it automatically connects the ground. Shorting. All right, so yeah, it looks like this. So you have screws. These screws here would go. You do 1 to 5, and then to ground, and then you'd already have a ground wire connected here. So there's that. Here we're looking at our phasing as well, and we're making sure in this that not only does it match our relay one line, but we're kind of doing a double check of our relay one line to say, do our zones overlap, right? Is P1 overlap here? They have B1 on the inside. Is that copacetic, I guess? And then making sure here's our ground. That's good. Wrong symbol. Here's where they missed the ground. That's just as bad. So they got dinged for that one. And then we're looking at our VT connections as well. Their VTs, they don't show on the AC schematic, but they do show it on their wiring, their juncture box wiring. So I did pull that up. And here they just have the ABC labels. This is a back check, so not everything is actually, sorry. They used the wrong standard, so I didn't finish checking that. That's why it's not highlighted. And then here's an example of some of the wiring, and this is showing the highlights where I was making sure this matched the schematic, and then once I checked that, I was able to check the wiring as well. So that is pretty much it for the presentation. So any questions or comments, feel free to email me at adam.benedict@poweremg.com. With that, I thank you for your time. Thanks.